Okay, hello everyone. Welcome to exercise class 6. So today in this exercise class, we will be solving two equations, two Laplace equation, mainly using separation of variables. The first one, I recommend you to do it after finishing the question 1 of problem set 6, because in this question, it's solving the Laplace equation in cylindrical coordinate, which you will use some special function, the special function. So in problem set 6, the first question, you'll be asked to solve, to do the separation of variable and derive the special function. So if you haven't finished that question, you won't be understand what I'm doing next, or you can't even do this question. So for question 2, you'll be asked to solve the Laplace equation in spherical coordinate. Okay, so again, make sure you try both questions before going to the solutions. This time, the questions are a little bit hard, and some of it are out of the syllabus. So it's okay if you struggle and don't know how to solve it. Okay, so let's go directly to the solution. So first of all, for question 1, we have to consider a cylinder, with height L and radius A. And for this cylinder, the bottom and the side, the potential of the bottom and the side are fixed to be 0. And for the top face, okay, so radius A, height L, and for both the side and the bottom, the potential is fixed to be 0. And for the top face, the potential is given by a general function, f as a function of rho and phi. Okay, so let's first of all recap a little bit what we have done in the question 1 of problem set 6. So let's write down the Laplace equation. Okay, let me use another color. So let me write down the Laplace equation in cylindrical coordinate. So okay, so just a quick recap of the question 1 of problem set 6. So first of all, whenever you have to deal with the puzzle, this kind of puzzle differential equation, the first step is to try separation of variables. Okay, so for the details, you can refer to problem set 6. And basically what you did is you separate the function, the potential, as 3 separate function, which depend on phi only, rho only, phi only, and z only. Okay, so after you separate into 3 functions, you can obtain and plug them into the PDE. You can obtain 3 independent, not really independent, but 3 separate the ordinary differential equation with some extra constant k and m. So these 3 equations are the ODE you obtained after separation of variable. So right now you just have to solve the ODE one by one. So for the first two ODE, it's quite easy to solve. So for the first one, the function of set is basically just exponential function. The solution is basically just exponential function, or you can write it as hyperbolic sine or cosine. And for the second ODE, the solution is basically the linear combination of sine and cosine function. So here, C, D, E, F are the constant in the solution. But for the last ODE, the solution is not trivial. Actually, this equation is called the Bessel equation. So we have a name for it, and also the solution. Again, you guessed it is the Bessel function. So usually the Bessel function P of rho is equal to. So it's a linear combination of two Bessel functions: the Bessel function of the first kind, Jm, and also the Bessel function of the second kind, Yn. Okay, so in problem set 6, you are asked to solve it using power series. So basically expand a power series and solve to find the Bessel function. So here I write down the Bessel function in terms of power series. Okay, here the first one is the Bessel function of the first kind. Okay, just a second. So this one is Bessel function of the first kind. And for the second one, another linearly independent solution is also constructed by the Bessel function of the first kind as this. Oops, sorry. Okay. Okay, so this one is the Bessel function of the second kind. So these two are two linearly independent solutions of the Bessel equation. So, and also notice that so far you don't have any constraint on the constant k and n because we haven't put in any boundary condition in it. Okay, so after we obtain those functions, we can write down the general solution of the Laplace equation in cylindrical coordinate. So actually this one is also given or you are asked to derive it in problem set 6. So here we are summing over all possible m and k with each terms are those three functions multiplying together. So for every m and k, we have a set of constant a, b, c, d, depending on the boundary condition we imposed later on in the questions. Okay. Okay, so this is the full form. And before I plug in the boundary condition, I would like to introduce more about Bessel function because well, you have to use the following properties in order to obtain the solutions. So, okay, Bessel function. So the first, again, for the following, for all the properties of the Bessel function, I think is out of the syllabus, but so I will just go through it very quickly without deriving anything. So the first thing, the first property I want you to notice is the asymptotic forms. Asymptotic forms of the Bessel function. So first of all, we consider very small x, very small parameter. So in that case, the Bessel function of the first kind Jm is actually roughly proportional to x to the power n. Basically, just use the original power series form, and since for small x, the lowest order will dominate, so you just get rid of all the higher order terms and left with the lowest orders. And so you'll find that when x is close to 0, Jm behave fairly well. It tends to 0. However, for the Bessel function of the second kind, okay, the asymptotic behavior is quite complicated. So for m equals to 0, okay, just a second. So for m, the first one is for m equal to 0, we have this form. Natural log of x over 2 plus some constant. So I won't derive this form and this constant here, but I can give a name of this constant. So if you're interested, you can Google it for more detail, or you can email us. Okay, so this one is for m equal to 0. And for m not equal to 0, the asymptotic behavior is like this. It's proportional to 1 over 1 over x to the power m. So this is for m not equals to 0. So you can see that from this term, from the second one, the Bessel function of the second kind actually is singular at x equal to 0. Okay, so that's the first one, the first asymptotic behavior. And for the second one, for very large x, both Jm and Ym behave like an oscillation with damped amplitude. So Jm is basically a cosine, behave like cosine with a damping amplitude, and also Ym behaves like a sine. Okay, so for these two terms, they're just oscillation, behave like an oscillation with damping amplitudes. So what does it tell us? So that means that for Bessel function, we have infinite number of roots, because eventually for the tail of the Bessel function is behave like sine or cosine. So you know that for sine or cosine, they have infinite number of roots. So from that, we know that Bessel function also have infinite numbers of roots. So for Jn for Bessel function of the first kind, I defined x m n as the root as the n root of as the n root of Jn of x. So n goes from 1 and on and on and on, because there are infinite number of roots. Okay, so keep in mind of these two properties. The Bessel function of the second kind is singular at x equals to 0. Oops, highlighted. Okay, and also for the Bessel function, we have infinite number of roots. Okay, so now we can go to solve the PDE by plugging in the boundary condition. So let me just copy the general solution down here. Okay. Oops. Copy and paste. Okay, great. Okay, so the first boundary condition it actually is not necessarily a boundary condition. The first one you may notice is that in the general solution, we have the Bessel function of the second kind here. And since for the region we're interested, we are finding the potential inside the cylinder. So the Bessel function of the second kind is singular at rho equal to 0, which is not definitely not possible for potential. So we know that the coefficient of this term must be 0, because we can't have singular values potential. And for the second boundary condition, the bottom of the cylinder, the potential of the bottom of the cylinder is 0. So we can plot Z equal to 0 into the general solution. Okay, so it is a little bit long, so let me write that down. So the Bessel function of the second count is out, so we left only with the first count. And we keep the sine and cosine term here. There's nothing we can do it for now. And we can then plug in Z equal to 0. So for exponential e to the power of 0, just basically 1. So we left with the two coefficients, E and F, these two equations. Okay. Highlight. Okay. So notice that we still have two variables here, rho and phi here, which means that this equation is valid for any values of rho and phi at the bottom of the cylinder. Which means that the highlighted part, E plus F, must equal to 0 in all the cases. Because the only solution for this one, the first part, the Bessel function and also the sine and cosine definitely not 0 for any rho and phi. So the only thing we can set 0 is the last term, E plus F. So we have E plus F equal to 0. So now we can find we can know this relation. Okay, which also means that for the set dependence, you can basically just write hyperbolic psi of k set, because exponential k set plus e to the power of minus k set, where it's just parabolic function. Okay, for the third boundary condition, we have the potential of the side of the cylinder equal to 0. Okay, so again, we plug that into rho equal to 0, rho equal to A, plug that into our general solution. Okay, so for the set part, I'll replace it with hyperbolic psi, and also we left with the sine and cosine term here. Okay, again, this equation is valid is true for any values of phi and z. So we must have this term equal to 0. Okay. So as I mentioned before, there are infinite number of roots for Bessel function. So we have Ka is equal to the root of the Bessel function, xmn. So here, where xmn's are the roots. Okay, so we have this one. And since we have infinite number of roots, so we have n's go from 1 to infinity. Then we can put a constraint on the constant k. So now we know that not all possible k are all is we know that not any k values is can fulfill the boundary condition of this equation. So k must satisfy this condition in order to satisfy the boundary condition. Okay. Also, we know that the potential must be single valued. So when you go the full circle 2 pi and come back to the original phi, well, it must equal to itself. That means that m must also be a positive integer. Because we are dealing with the sine n phi and cosine n phi there. So again, m runs from 1 to infinity. So now we have a much shorter form of our solution. Okay, m and go from 1 to infinity. Okay, maybe I write 2 summation sign. And now we only have 2 constant unknown. So I rephrase it. I put the constant, the coefficient of cosine and sine be a and b, because we only have 2 constant to fix now. So in order to find these 2 constants, we have to impose the last boundary condition, which is when z equal to L, we have the potentials equals to a general function. f of phi, f of rho and phi. So again, we plug z equal to L into the solution above. So I'm not writing the, for the summations, I'm not writing the boundary, the lower bound and the upper bound for m and n, because you all know that those goes from 1 to infinity. So we put z equal to L here. And for the other stuff, yeah, remains unchanged. Okay. So in order to find the coefficient A and B, we have to use the orthogonality condition of Bessel function and also for sine and cosine. And I'm sure that all of you have learned Fourier series. So you know sine and cosine have some orthogonality condition. So I'll just write that here. For sine n phi and sine n prime phi, if you multiply them and integrate it from 0 to 2 pi, if it will give you a delta function multiplied by m. So if m and n prime are equal, it will be pi, and if not, it will vanish. And same for cosine and cosine. And for sine and cosine, when you integrate it, it will always be 0. Okay, so that's the orthogonality condition for the Fourier series. And for Bessel function, it still has some similar orthogonality condition, have a similar form. So if you integrate two Bessel function, here Bessel function, in the Bessel function, it is depends on two different roots. Okay, xm and xm prime, and multiplied by rho and integrated over from a from 0 to a, you will obtain this constant with, again, a delta function. So for this term, xmn over a, sorry, xmn over a is actually the k we are using here. So in order to find the coefficient, first of all, let me first copy the whole the solution we have obtained. Okay. First of all, we multiplied it with another Bessel function, this time with different k. With different k, m, n prime. And for the others, they remain the same. Okay, should be a, m, n cosine m phi plus b, m, n sine m phi. And then, just like the orthogonality condition above, you multiply it with the Bessel function, and also multiply the row integrated from 0 to A. And that you perform the same operation on the right-hand side. So again, multiply with a Bessel function and row. And for the right-hand side, we have the function f here. Okay. So for the left-hand side, after you perform the integration. So here I highlight using color red here. In that integration, you can separate out all the row dependence. So basically, the row only depends on. Okay, maybe I'll write it in a separate line. Basically, you can single out again. Summation go first, and you can plot that. Move all the function that depends on row inside the integral and put everything else out. So we have the hyperbolic side outside the integral and also the sine cosine outside the integral. So again, I will keep the right-hand side untouched. Okay. And here now you can use the orthogonality condition, since that because for all just like the Fourier series, for n not equal to n prime, this term will vanish and only left with n equals to n prime. So for the whole summation of n, we basically just select one Bessel function. Okay. And get rid of the summation of n, one summation. And the only thing left is the normalization constant. In the color blue. And again, for the right-hand side, you can't really do anything about it because f is a general function. You don't know the details. And after that, the only thing you left is sine and cosine, sine n phi and cosine n phi. And in this stage, all you have to do is perform Fourier to do the Fourier series and find out the coefficient of am n and bm n. So I'm sure that you all know how to do a Fourier series. So I will just write down the answer here. So for the hyperbolic side, you move it to the right-hand side and become a hyperbolic cosecant. And for the normalization constant, you move it to the right-hand side as this. And also for the right-hand side, you have the original integral. And this time with an additional term because you also perform, you do the Fourier series. Okay. So left with the term inside is for A, because EMN is the coefficient of cosine n phi, so you have to multiply cosine n phi in order to get, obtain the coefficient. And also, don't forget the normalization constant for the Fourier series. You have an extra pi on the left-hand side after the integration. So when you move it to the right-hand side, it becomes 1 over pi. Okay. Similarly, for B, you just have to replace cosine with sine. So for B, you just have to replace it with sine. So here, you obtain the coefficient rewards. So for any general function f, you just have to, once you obtain the analytical form or the algebraic form of f, you just plug in the integral, perform the integration, then you can find the coefficient of amn and bmn. And after you calculate the coefficient, you plug in into the general solution. We have found general solution of the potential we have found. Then you can find the potential of this equation. So here, as you can see, the blue part is correspond to the Bessel series, and the red part correspond to the Fourier series. So that's it for this question. So for the second questions, we have two hollow sphere. Okay, let me draw the sphere first. The inner sphere have a radius A, and the outer sphere has the radius B. Okay, so this is the Z axis. Z axis, and for the inner sphere, the radius A, and for the outer sphere, the radius B. And this sphere is divided into horizontally into two parts. So, okay, so in this question, you're asked to, they given the potential on the inner sphere and the outer sphere, and you're asked to solve the potential in all in every regions. So first of all, let me write down the Laplace equation for spherical in spherical coordinates. And I'm sure that Professor Johnny have covered this the Laplace equation in spherical coordinates during the lecture. So I think you all have already known the general solution of this equation, which is, so here is the general solution. Which is for the R dependence, which is a power series of a polynomial of R, and also sine and cosine of m phi, and also for the theta part is the associated the gender polynomial P, L, M. And since this equation is a asymptotically symmetric, asymptotically symmetric, which means that the configuration is independent of phi. Okay, So it doesn't matter whether you put phi equal to 0. So the whole solution should be independent of phi. So you can write, if there's no phi dependence, m obviously be equal to 0. Okay. So for the associated Legendre polynomial, it becomes the just Legendre polynomial, PL. And I guess here I don't have to write m equal to not equal to 0. So for all n and l, but for m equal to 0, we don't have the sine and cosine parts, sine and cosine of the phi part. Okay. So right now, if this solution is independent of phi, so the general form of this solution is much simpler. And we also given two boundary conditions, one on the outer sphere, called it V1. So V1 is given by 0 on the upper atmosphere, and V, constant V, as the lower atmosphere. And I called the boundary condition at the inner sphere V2. Again, this time reversed V as the upper atmosphere and 0 as the lower atmosphere. Okay, so for this solution, we have to divide it into 3 different regions, 1, 2, and 3, because the boundary divide those the whole space into 3 regions. So we have to solve the solution for these 3 regions separately. So for region 1, R greater than B. So for if we consider R goes to infinity, the R to the power of L term obviously also go to infinity. So which it means that AL, the constant AL, the coefficient AL must equals to 0. Otherwise, the potential will grows to infinity. So what we left with for the region 1, the potential, what we left with is just BL multiplied by R 1 over R to the power of L plus 1, and also the Legendre polynomial. So again, we have to consider the boundary condition. We have to plot R. We have to consider at R equal to B, we can plot the boundary condition in. Okay, what happened is when R equal to P, we can plot that in. Equals to V1. And I think it should be taught during the lecture, but the Legendre polynomial also have some orthogonality condition, which I will write it here. Orthogonality condition. So if you multiply to the Legendre polynomial PL and PL prime multiplied with sine theta and integrated from 0 to pi, you obtained 2 over 2L plus 1 multiply the delta function L, delta L prime. So again, in order to find BL, you perform the same trick, integrate the whole thing from pi, from 0 to pi, where the integram is multiplied by another Legendre polynomial and also sine theta. And you do the same thing for the right hand side. Okay, so we have V1 here. So in the left hand side, what we left is, well, we can move BL and B to a power of minus L minus 1 outside the integration. And for the integration, what we left is just the normalization constant, 2 over 2 L plus 1. And for the right hand side, since V1 vanished at the upper atmosphere from 0 to pi over 2, so for the whole integration, we just we only have to consider, okay, let me use the color blue. We only have to consider the integration from pi over 2 to pi. And we can replace V1 with V. Okay, again, we can do the method of use the method of substitution. That x equals to cosine theta. Then the whole thing will becomes, we can move V outside, and then the whole thing will become integrating PL of x dx from minus 1 to 0. Okay, so now we have BL. We can move all the other constant to the right hand side. Then we can obtain this integral. And also notice that the Legendre polynomial, if L is odd number, then the Legendre polynomial is odd function. And if L is even number, then the Legendre polynomial is even function. So whether the Legendre polynomial is even or not depends on whether L is even or not. So we have this, oops, this should be minus x. We have this condition here. We have this property here. So for L is even number, minus 1 to the power of L is just 1. So we have P of minus x equals to P of x. So basically just a property of even function. And the same goes for the odd number L. So why we do that? Because we can change the boundary of the integration from 0 to 1 to from minus 1 to 0 to 0 to 1. And we can consider different values of L. For L equals to 0, this P0 is just 1. So the whole integration is just 1. But for L greater than 0, there is a property of a Bessel function, P of L is equals to, is related to P of L plus 1 and P of L minus 1 by this. So this one is also out of the series. So you don't have to, unless Professor Johnny mentioned this property during lecture, otherwise you don't have to worry. You have to worry that you have to deal with it during the midterm or exam. So just for information, so using this property, we can perform an integration on both sides. Well, the right hand side is basically differentiating it and then do the integration. So we just have to plug x equal to 1 and 0 on the right hand side. So we have this. And also for any order of the general polynomial, p of 1 is equal to 0. So these two terms always equal to 0 no matter what L we use. So we only left with these two terms. Okay, so now we know that for L equal to 0, the base 0, when we plug 0, L equal to 0 inside the integration, okay, move down a little bit. Then we plug L equal to 0 inside the BL we find above. You can just obtain BV over 2. And when we plug the integration back to the form above, we can obtain this constant. Okay. Moreover, for odd number L, since PL is an odd function, P zeros must equal to 0. That means for even number of L, because BL is dealing with the general polynomial of order L minus 1 and L plus 1. So for even L, BL is equal to 0. Now we have found the coefficient. We can write down the final form of the potential of the first region. So we have 1 over R dependence here. And when we plot it, since we consider only odd number L, so the minus 1 to the power of L will always be minus 1 because of power. So we have the minus here. So I move the minus outside the summation, and L is summing all possible odd number. And by the way, I also move the V over 2 outside the summation. It's just a constant. And after I plug everything back in, we can obtain these expressions. And that's the general solution. That's the solution for region 1. And also, the treatment for region 3 is also similar. For region 3, so let me skip region 2 from now and do the region 3 first. Again, for R tends to R goes to 0, anything proportional to inversely proportional to R will be singular, which means that BL this time is equal to 0. So what we left is AL. Okay, again, we consider boundary condition as R equal to A. Substitute it in. A to the power L okay, then is equals to V2, the boundary values of the inner sphere. Again, we perform we use the orthogonality condition and perform the integration of both sides with the Legendre polynomials. We get all the thing is just similar to the solution of region 1, except for this time we are finding the coefficient of AL instead of BL. Okay, and also for this time, for V2, it vanished at the lower hemisphere. So the integration goes from 0 to power 2. And after I substitute x equal to cosine theta into that integration, we have the integration goes from 0 to 1, integrating the Legendre polynomial. Again, it's just copying. You can just copy in the solution above, which is this one. This one is for L greater than 0, and for L equal to 0, we have simply not V over 2, V only. Okay, so now we have to find the coefficient of the coefficient AL. For L equal to 0, it's just V over 2. And if L is even number, well, it's basically vanished as equals to 0. And if L is an odd number, we obtain the form similar to the form above. Okay, this is 2 here. So after we plug those things back in, we can obtain the solution of region 3. Again, let's summing over all the odd number L here. Okay, so this is the solution of the potential at region 3. Okay, and for the potential at region 2, it will be a little bit more complicated than region 1 and region 2, because for region 2, complicated than region 1 and region 3, because for region 2, we have two boundaries, both the inner sphere and outer sphere. So let me just first of all copy the general solution of the Laplace equation here. Okay, so now we cannot just ignore AL or BL because we have two boundaries here. We have plugged in two boundary conditions. So first of all, let us consider R equal to B. When we plug R equal to B here, so R equal to B here, and also R equal to B here. When R equal to B, it's the boundary condition is equal to V1, and again we perform the same trick. Integrated over the Legendre polynomial, and the same for the right hand side. And I think now you have already know what this is. So for L equal to 0, it's basically just V, and when L is greater than 0, it is the same thing in same thing you obtained in region 1. Okay, and also similarly for at R equal to A, well, I just write down the form here. Again, you substitute R equal to A here, and again perform the integration. So you obtain V on the right hand side if L equal to 0, or this term if L is greater than 0. So now both AL and BL are not 0, and we have to find it using these two equations. Now we have a pair of simultaneous equations. So first of all, let's consider an easier case, L equal to 0. It's basically just, well, b to the power of 0 is just a 1, and b to the power of -1, so it's just 1 over b, which is equal to v over 2. Well, because after we move the 2 over 2l plus 1 to the right hand side, well, it's because it becomes 1 over 2. And similarly, for the second equation, we have a naught plus b naught over a, also equal to b over 2. So obviously, a naught equal to b over 2, and b0 equal to 0. Okay, easy. And for the next case, L greater than 0, we have this pair of simultaneous equations. Okay. Let me write it down. Oh, oops, this one should be a to the power of L. Okay, so for this pair of equations, the solution is not that trivial, but I believe that, well, it's just simultaneous equation. You can do the algebra. So here, I just write down the solution of AL and BL. It is related to A and B and L as this way. Okay, So this is the solution of AL, and for BL, well, after you can just simplify it as this. Potential is 1 of charge. Anyway, we are almost done here. Okay. So this is the solution of BL. Okay, one final touch here, because we all know that for this term, the highlighted term, it will vanish if we consider odd number L. So again, consider only odd number L for odd number of L. Well, we can also change the -1 to the power of L to basically -1. We can simplify that. So right now we can plot all AL and BL into the general form of the solution. And okay, you can, after some simplification, you can obtain this solution. Okay, the solution consists of a lot of terms here. So here is the to the power of L minus L minus 1 term. So, and here is the R to the power of L term. Over this term. Okay, so this is the solution of the potential in region 2. So right now, we have found all the potential in both region 1 and 2 and 3, and that's the solution of question 2. Okay, so that's it for today's exercise class. So thank you all for the attentions. I understand for this exercise class, the algebra is a little bit complicated. So if you cannot follow, or if you have any questions, feel free to email us. So that's it for today's exercise class. Thank you very much. Goodbye.